So I'm doing my deep dive on the diverse properties of the Fibonacci sequence. So a quick overview of what I will be talking about is first the history of Fibonacci and the sequence, of course, how it works, some unique properties it has, and the relevance it has to biology. So to begin, the Fibonacci sequence was used and discovered in India in the 6th century. However, Fibonacci was a European who discovered it, so now it's called Fibonacci sequence. He was a 13th century Italian mathematician, and he traveled around North Africa, and his main contribution that we know of today is the Fibonacci sequence, but he really helped advance European mathematics by pushing the Hindi-Arabic numerals, which allowed European mathematicians to do more with calculating and just mathematics in general. He actually discovered the Fibonacci sequence by doing a problem called Liber-Abaci, and he noticed it while recording the growth of rabbits. So he noticed basically 1 and 1 together is 2, and then 1 plus 2 is 3 by counting rabbits. So he made up the formula, Fn, n being the number in the sequence. So if n equals 3, it would be not 0, not 1, but 1. And then equals Fn minus 1 plus Fn minus 2. So how it works is 0 starts kind of up, 0 and 1, and you add the two consecutive numbers which equal the next. So the sequence goes 0, 1, which isn't listed, then 1, 2, 3, 5, 8, 13, and so on. So you can see 0 plus 1 equals 1, and so you take that 1 and you add it to the new one. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on, and it keeps going on forever. So another unique property it has is if you square the Fibonacci numbers, you get 1, 4, 9, 25, 64, and 169. So all of those are not Fibonacci numbers. However, if you add the squares up together, they equal 8 times 13, excluding the 13 squared. So it equals the number it ends in times the next number. And another way to explain it is if we visualize them with boxes. So in the picture on the slide, there's boxes with areas in them. So the one that has 8 is 8 squared, 5, 5 squared, so on. But another way to find the area of a rectangle is width times height. And so here you can see that the height is 8 and the width is 13, which equals 8 times 13. But also you can see that the area is 8 squared plus 2 squared plus 1 squared plus 1 squared plus 3 squared plus 5 squared. If you do this and you connect them using a line, you get a nice spiral, as you can see right here. Remember this spiral, and it shows up a lot in nature. So the golden ratio is also found in the Fibonacci sequence. So first of all, the golden ratio is an irrational number that is often used for like visual aesthetic, and it's used a lot. It's an important number, and its importance is because it's irrational. So it's illustrated by phi and is about 1.618, we'll say. And there's a bunch more numbers, but so the Fibonacci numbers can be used actually to estimate the golden ratio. So if you take the ratio of two consecutive numbers, you get about the golden ratio. And interestingly enough, the higher the Fibonacci numbers are, the closer the ratio is to the golden ratio. So for example, 21 divided by 13 equals 1.619, which is pretty close, but still off. But if you take 377 divided by 233, a higher Fibonacci number, you get 1.618. And the higher you go, the more decimal places are correct. So now that the Fibonacci numbers can be used to estimate the golden ratio can also be used to find Fibonacci numbers. So you have this formula, Fn equals phi to the n power minus 1 minus phi all to the n power divided by the square root of 5. So why it's important to me is because I find biology fascinating, and it is seen everywhere in biology. It's seen in how things grow. And one of the main reasons for this is because multicellular organisms all grow in a similar fashion. So specifically, cells divide asymmetrically, and they also follow a temporal and spatial rules. So temporal meaning they grow in an organized fashion. They grow, they replicate, they split. They grow, they replicate, split. They grow, replicate, split. They also grow in a spatial. They want to maximize their cell growth. The Fibonacci sequence does both of these things. It's both an organized sequence and it maximizes growth. Whereas if you grew in a straight line, you would have many gaps. So for example, if you follow my mouse, if you grew in a straight line, it would just be like this. But they're growing in spirals, so they're maximizing space and more lines can follow. Same with these, and you can see them, all the spirals. It's even found in fingerprints because of how the cells grow. They all grow in the same fashion. Not only do the cells grow, but at a molecular level, the double helix in DNA also contains Fibonacci-like properties. Since the double helix is a spiral, it's not a perfect spiral, it's off a little bit, but it does this because nature grows in the Fibonacci sequence. And here are my citations. Thank you for watching.